Welcome back to the deep dive. Usually when we start these conversations, I like to ease us in a bit.
Right.
We might start with a fun historical anecdote, or maybe a curious fact about the animal kingdom.
Just to get the brain cells warming up.
Exactly. A rhetorical question, maybe? We like to set the table before we serve the meal.
That is the standard operating procedure, yeah.
But today is different. Today we are dispensing with the warm-up completely.
We really are.
We are wading into some truly murky waters right from the jump. And I don't mean that metaphorically.
No, not at all.
We're looking at a stack of documents here, articles, research papers, transcripts, and quite frankly, it reads like the opening chapter of a medical thriller.
It does.
And I don't say that lightly. I mean, if this were a movie script, I'd probably tell the writers it was a little too dark.
I know exactly what you mean. It is rare that we get source material that, starts in a funeral home and ends in high-level molecular biochemistry.
Yeah.
But that is exactly where we are today. We are looking at a phenomenon that is both incredibly visceral and deeply scientific.
We are talking about what's been called the embalmer's mystery.
Yeah.
This is the hook that grabbed me right away and just wouldn't let go.
It's hard to ignore.
It is. So, since roughly 2021, embalmers, and these are people who know human anatomy better than almost anyone, right?
Absolutely. They deal with the circulatory system every single day.
Exactly. So they started reporting something completely unprecedented.
Something very strange.
They weren't finding normal blood clots in the deceased. They were pulling out these massive white, rubbery structures.
Right.
Things that didn't break apart, things that look less like biology and more like, like industrial silicone.
Or white calamari inside the veins.
White calamari. That is such a disturbing image.
It is a visceral image, isn't it? But what we are doing today is moving past that shock value.
We have to.
We really do. If we just stay at the gross out level, we learn absolutely nothing.
Right. So what are we actually looking at?
Well, we have a set of data from a group of doctors in New Zealand who have actually analyzed these casts.
Okay.
And along with that, we have a very dense technical breakdown of the biochemistry behind what are being officially called fibrinoid microclots.
Fibrinoid microclots.
Or anomalous insoluble complexes. AICs for short.
Anomalous insoluble complexes. That sounds like engineer speak for we have absolutely no idea what this is.
It sounds that way, yeah, but it's actually very precise terminology.
Unpack that for me.
Okay, so anomalous because they shouldn't be there. They are completely foreign to normal human physiology.
Right.
Insoluble is the really terrifying part.
Because they won't dissolve.
Exactly. It means the body's natural chemical toolkit, the enzymes we rely on to clean up our blood, they can't break these things down.
Wow.
And then complexes means they are not just simple blood clots. They are a hybrid structure, a very strange mix of materials.
Okay, so here is our mission for this deep dive.
Yep.
We are going to deconstruct these things.
Piece by piece.
Right. We aren't just talking about the scary stories. We are talking about the hard chemistry. We need to know what they are made of, down to the molecular level.
We need to know why they are white.
Why they are white, why they are rubbery.
And crucially, we really need to understand the trigger.
The why.
Yes. Why did they start appearing? What is the catalyst for this? Because the sources point to some very specific viral proteins and bacterial components that act as the spark for this whole fire.
And perhaps most importantly for you listening right now, because let's be honest, if these things are forming in deceased people, the obvious question you're asking is, are they forming in me right now?
It's the natural question.
It is. So we are going to walk through the therapeutic degradation strategies found in the sources.
Right. Because if the body can't break them down naturally, do we have a manual on how to dissolve the undissolvable?
And do we?
The literature says yes, but it requires a very, very specific approach. It's not about just taking an aspirin and hoping for the best.
Okay, before we jump into that, just a quick tone check. We are going to be throwing around some heavy terms today.
Things like proteomics.
Proteomics,
Yeah.
amyloidogenesis.
Cystostochiometric.
Right, so don't panic.
Please don't panic.
I won't, because I have you here to explain it to me. We are going to break all of this down into very simple concepts.
We will.
But also, a quick disclaimer up front. We are reporting on the findings within these specific papers and transcripts provided. We are not giving medical advice.
Absolutely not.
We are just exploring the mechanisms described in these texts. If you're worried about your health, go see a doctor, not a deep dive host.
Precisely. We are here to analyze the source material.
Yeah.
And the story that material tells is, well, it's fascinating.
Okay, let's start with the visual. Section 1. The embalmer's mystery. When I think of a blood clot, I think of, a scraped knee
or nosebleed.
Right. Red, messy, scabs over eventually.
That is what we call a red clot. And in the medical world, that is the standard.
Okay.
A red clot is essentially a loose mesh.
Like a net.
Imagine a fishing net made of a protein called fibrin. It catches a bunch of fish, and in this case, the fish are your red blood cells.
God.
In fact, a normal red clot is about 60 to 80% red blood cells.
So it's mostly just blood cells held together by a little bit of protein glue.
Correct. And because it is a loose mesh, it is porous. It's squishy.
Like
Grape jelly, exactly. And importantly, your body has enzymes that can get inside that mesh and break it down when the wound is finally healed.
So it's a temporary structure.
It's temporary architecture. It's meant to stop the bleeding and then just disappear.
Now, compare that to these white clots, these AICs.
The difference is night and day.
How so?
Well, the sources describe AICs as dense, matted, and highly ordered. Structurally, they are rich in platelets and fibrin, but they are strikingly low in red blood cells.
How low?
We are talking less than 6% red blood cells.
Less than 6.
Compared to the 80% in a normal red clot.
So that's why they're white.
Right.
They literally don't have the red blood cells to give them that color.
Exactly. They are pale yellow or white. But the most disturbing part is the texture.
Right, the rubbery thing.
The New Zealand study describes them as elastic lumen-conforming casts.
Lumen-conforming. That phrase really stuck with me when I was reading the prep.
It's a very descriptive term. It means they take the exact shape of the tube they're inside.
The lumen being the inside of the vessel.
Right. The lumen is the inside space of the blood vessel. So if an embalmer pulls one of these out of a leg artery, it looks like a perfect rubber mold of the inside of that leg artery.
Wow.
It has the branches, the curves, everything.
See, that implies they didn't just drift there from somewhere else and get stuck.
No.
They grew there. They paved the road.
Yes, they literally mold themselves to the inside of the blood vessel as they grow.
That is wild.
The embalmers are pulling out structures that look like perfect replicas of the bronchial tree or the femoral arteries.
And they don't break when you pull them.
They are long, continuous, and rubbery. You can pull on them and they don't snap. They have actual tensile strength.
Unlike a normal clot.
A normal blood clot would just crumble in your hands. These snap back like a rubber band.
That is terrifying. It's like the vessel has been lined with, I don't know, silicone caulk.
That is not a bad analogy at all. And it brings us to the core scientific definition of what these actually are.
Okay.
They aren't just clots. They are amyloid structure.
Amyloid. Now, I've heard that word before, associated with Alzheimer's, right? Amyloid plaques.
It is the exact same concept.
Really?
Yes. In biochemistry, amyloid doesn't refer to a specific protein, but rather to a shape. It's a state of misfolding.
A state of misfolding.
Think of it this way. A normal protein is folded like origami into a very specific functional shape.
Okay.
It's flexible, it can move, it can do a job in the body. An amyloid protein has misfolded into what's called a cross-beta sheet.
A cross-beta sheet. So it's like the protein gets crumpled up into a locked position.
More like stacked. Think of it like stacking sheets of plywood. You take that flexible origami paper, you iron it perfectly flat, you stack 100 sheets on top of each other, and then you glue them together.
That sounds incredibly stiff.
It becomes incredibly stable, very hard, and very difficult to pull apart.
Right.
Normal fibrin is like a flexible rope. This amyloid fibrin is like a stack of plywood sheets glued together.
And how do we know for sure that these white clots are amyloid? I mean, is it just a guess based on the rubbery texture?
No, it's confirmed by strict chemistry. The sources discuss a specific test called the glow test.
The glow test.
Using a stain called theoflavin T, or THT.
DHT.
Theoflavin T is a fluorescent stain that specifically binds to those cross-beta sheets I just mentioned.
It looks for the plywood.
It loves that plywood structure. If you pour it on a normal red blood clot, absolutely nothing happens. It doesn't glow at all.
Right.
But when they applied it to these fibrinaloid microclots, they glowed bright green, bright neon green fluorescence under a UV light. That is the gold standard proof in biochemistry that you are dealing with an amyloid structure. It proves definitively that the protein has fundamentally changed its architecture.
It's not just a clot anymore.
No, it's a misfolded protein aggregate.
Okay, so we have these rubbery, white, glowing casts. But here is the skepticism I can hear from you listening right now, and honestly, from myself when I first read this.
Sure.
These were found by embalmers in deceased people.
Right.
How do we know these didn't just form after the person died? You know, blood pools, things get weird post-mortem. Maybe this is just what happens when you leave a body for a few days.
That is exactly the first question any pathologist would ask. Is this just a post-mortem artifact?
Right.
And the New Zealand papers address this directly with a key piece of forensic evidence.
Which is?
Something called the Lines of Zahn.
The Lines of Zahn. That sounds like a sci-fi novel. Or maybe an obscure prog rock album.
It does, but it's actually classic pathology.
Okay, what are they?
When a clot forms in a vessel where blood is currently flowing, meaning the heart is actively beating and pumping it, forms in distinct layers.
Okay.
You get a layer of platelets, then a layer of fibrin, then another layer of platelets.
Like a sedimentary rock.
Exactly like sedimentary rock. It creates visible laminations, like the rings of a tree.
And these lines, these laminations, they only happen if the blood is moving.
Correct. If blood just pools after death, it clots in a big, homogeneous blob. It looks like that grape jelly we talked about.
Because nothing is flowing to deposit the layers.
Precisely. It doesn't have layers. But the clots analyzed in these papers clearly showed these lines of Zahn.
Which implies?
Which implies, definitively, that these clots formed while the person was still alive.
Wow.
They were growing inside the vessels, layer by layer by layer, obstructing blood flow while the heart was still actively beating.
That is a very heavy realization. It means this isn't just some weird post-mortem curiosity for morticians.
No.
It's a pathology. It's a disease process happening right now in living people.
And that leads us to the big question. Why didn't the body stop it?
Right.
Our bodies are amazing biological machines. We have enzymes specifically designed to eat clots. If I cut my finger, it clots, but a week later, the clot is gone.
So why can't the body eat these white rubbery things?
This takes us right into section 2, the bizarre chemistry, or as I like to call it, why they are indestructible.
Indestructible.
They are nearly indestructible to the body's natural defenses. And there are 3 main reasons for this outlined in the sources.
Okay, let's go through them.
The first is what we call the structural fortress, or the pore size problem.
Break that down for me.
Okay. To dissolve a normal clot, your body sends in an enzyme called plasmin.
Plasmin.
Think of plasmin as a little microscopic Pac-Man. It needs to chew up the fibrin mesh.
Right.
In a normal red clot, the mesh is very loose. The fibers are about 15 to 100 nanometers wide, and there are massive gaps between them.
So the Pac-Man has room to move.
The Pac-Man can easily swim inside the clot and start eating it from the inside out. Easy access.
Open gates.
But in these fibrinolytic aggregates, the fibers are completely matted together. They form a dense, solid wall.
How tight is the mesh?
Well, the source material explains that while the clots themselves can be huge, up to 200 microns or even centimeters long, the mesh itself is so incredibly tight that it is effectively impermeable.
So the Pac-Man simply can't get in.
Physically, the enzyme is just too large to fit through the holes in the mesh. It's literally bouncing off the surface.
Wow.
It's like trying to clean the fibers of a carpet with a toothbrush, but you can't even touch the fibers because there's a solid sheet of glass laid over them.
But purely physically, they are completely armored.
But it gets worse.
Of course it does.
It's not just a physical wall. There is a chemical trap built in. I call this the Trojan horse defense.
Oh, I read this part in the prep. This is genuinely diabolical.
It is biochemically fascinating and terrifying at the same time. The clots actually trap the body's own inhibitors inside them.
Inside the clot.
Inside the clot. Specifically, proteins called alpha-2 antiplasmin and PAI-1.
PAI-1.
Yeah.
That's plasminogen activator inhibitor, right?
Yes. PAI-1 is basically the stop signal for clot breakdown. It tells the body, hey, don't dissolve this yet, we still need it.
Okay.
These amyloid clots act like a sponge. As they form, they soak up all the PAI with alpha-2 antiplasmin from the blood and lock them inside their structure.
So let's go back to that fortress analogy.
Sure.
Not only is the wall too high and tight for the Pac-Man to climb through, but the fortress has also essentially captured the Pac-Man's arch nemesis and stationed them right on the walls.
Exactly. Even if a little bit of plasmin manages to get near the surface of the clot, it is immediately neutralized by the inhibitors trapped right there.
The clot is actively defending itself.
It is actively neutralizing the body's attempts to dissolve it.
That completely explains why they persist for months or even years.
It does. And then there is a third anomaly that is perhaps the strangest one of all, the alien fingerprint.
The alien fingerprint. This was the elemental analysis from the New Zealand findings, right?
Yes. They took these clocks and put them through a mass spectrometer to see exactly what basic elements they are made of.
Okay.
Now, normal proteins are made of amino acids, and a lot of those contain sulfur. Sulfur is a key elemental marker of biological protein.
Right. Sulfur bonds are what hold a lot of proteins together.
Exactly. But when they analyzed these white clots, they found they were severely depleted in sulfur, very, very low levels. However, they were massively enriched in phosphorus.
Low sulfur, high phosphorus. Why is that weird?
Because it's biochemically impossible for a normal, pure fibrin clot.
Impossible.
DNA is rich in phosphorus. Some cellular lipids are rich in phosphorus, but pure protein blood clots should be sulfur-rich.
So what does that mean?
The expert interpretation in the source is that this elemental profile suggests a hybrid organic-inorganic matrix.
A hybrid inorganic matrix. It sounds synthetic.
Or at the very least, fundamentally different from normal human biology.
Yeah.
It suggests that the body is being forced to construct something it doesn't even have the proper recipe for. It's improvising with whatever materials are floating around, creating a structure that is chemically distinct from natural tissue.
The source also mentions something called the proteomic puzzle regarding the ratios.
Right. The ratios of the protein chains. Fibrinogen, which is the precursor to fibrin, has 3 specific chains: alpha, beta, and gamma.
Okay.
In a normal, healthy human, these are present in a strictly 1-to-1-to-1-to-1 ratio.
1-to-1-to-1.
It's a perfectly balanced tripod.
Simple geometry.
But in these specific clots, the mass spectrometry showed a ratio of 1-to-7-to-3.
Whoa. 1 alpha, 7 betas, 3 gammas.
Yes. The recipe is completely broken. It's like trying to build a car on an assembly line, but you have a blueprint for 1 wheel, 7 doors, and 3 steering wheels.
The resulting structure is going to be a monstrosity.
Exactly. And that's what we're seeing. A twisted, misfolded, amyloid monstrosity that the body doesn't recognize.
So we have established that these things are real.
Yes.
They form in living people.
Yes.
They are physically and chemically armored against our immune system, and they are made of a warped recipe.
All true.
So the trillion-dollar question is, how does this start? What is the trigger?
This brings us perfectly to section 3, the catalysts.
Let's get into it.
The sources are very specific about this. They identify the transition of normal soluble fibrinogen into this zombie amyloid sludge as an induced pathological process.
Meaning it doesn't just happen randomly on its own.
Right. It requires an external trigger to force the misfolding.
So what induces it?
The primary trigger identified across the literature provided is the S1 subunit of the SARS-CoV-2 spike protein.
The spike protein. We've all heard so much about this specific protein over the last few years.
We certainly have. And specifically here, the research shows that the spike protein interacts directly with fibrinogen in the blood.
It binds to it.
It binds to it, and when it binds, it causes a conformational change. It physically twists the fibrinogen into that exact cross-beta amyloid shape we talked about earlier.
So the spike protein is basically the pair of hands that folds the origami paper wrong.
That is a perfect way to visualize it. Precisely. Yeah. And here is the really concerning part regarding the quantity of spike protein needed.
Okay.
The effect is described as substoichiometric.
Substoichiometric. We got to unpack that. That's a $5 word if I've ever heard one.
It is. So in chemistry, if a reaction is stoichiometric, you need exactly 1 molecule of A to change 1 molecule of B.
A 1-to-1 ratio.
Exactly. Substoichiometric means you only need a tiny amount of A to change a massive amount of B.
Whoa.
It acts as a catalyst or a seed.
A seed, like when you're growing a crystal.
Exactly like growing a crystal. You drop 1 tiny seed crystal into a supersaturated solution and the whole jar instantly turns to solid rock.
Wow.
The source claims that tiny, minuscule amounts of spike protein can trigger a massive cascading chain reaction in the fibrinogen, turning massive amounts of it into amyloid sludge.
Which brings us to a very sensitive topic mentioned heavily in the New Zealand doctor's report, the vaccine hypothesis.
Yes, and we need to be very precise and impartial about what the source material actually says here.
Right.
The New Zealand doctors note a strict temporal correlation. They observed that these unique, massive white clots started appearing in large numbers in embalming rooms in 2021, which correlates temporally with the global vaccine rollout.
So they're connecting the dots between the genetic platforms and the spike protein.
Their logic, as outlined directly in the transcript, is this. The vaccines are explicitly designed to induce the host, that's you, the patient, to manufacture the spike protein.
Right.
If the spike protein is the known molecular trigger for these amyloid clots, and the genetic platform makes your body produce that spike protein, then they argue there is a potential causative link.
And they are calling for an investigation into that link.
A rigorous, urgent investigation. They argue that if we cannot precisely control how much spike protein a person produces after receiving the platform, or how long they produce it for, we might be inadvertently setting off this exact clotting cascade in susceptible individuals.
It's a really important distinction, though. They aren't saying everyone gets this.
No, not at all.
They are saying we need to understand the underlying mechanism.
Correct. It's entirely about understanding the risk and the mechanism.
But it's not just the spike protein that can do this, is it? The source mentions some bacteria, too.
Correct. It's not exclusive to COVID-19 or the genetic platforms.
Right.
Bacterial components, specifically something called lipopolysaccharide, or LPS,
LPF.
which is found in the cell walls of gram-negative bacteria. LPS is also a highly potent trigger.
How potent?
In fact, the research shows that one single molecule of LPS can affect 100 million fibrinogen molecules.
1 to 100 million. That is explosive.
It creates a massive autocatalytic seeding event.
Yeah.
And this actually explains why some people with severe chronic bacterial infections might also suffer from these microclotting issues.
Because the bacteria providing the seed.
Exactly. It's a generalized mechanism of inflammation gone terribly wrong.
And then there is the fuel to the fire, something called NETs.
NETosis. Neutrophil extracellular traps.
What are those?
This is actually supposed to be a defense mechanism. Your immune cells, specifically neutrophils, sometimes realize they can't just eat a foreign bacteria.
So what do?
They literally explode themselves and shoot out a massive web of their own DNA.
Like Spider-Man.
Very much like Spider-Man, exactly. They shoot out these sticky webs of DNA and histones to physically trap the invader.
Okay.
But in the context of these amyloid clots, the nets totally backfire. The sticky webs end up wrapping around the amyloid core.
So they reinforce the clot.
They act exactly like rebar in wet concrete. They make the clot even tougher, even stickier, and those webs actually help trap those chemical inhibitors we talked about earlier. The source explicitly calls this structural reinforcement.
So you have the spike protein starting the fire, twisting the fibrinogen into solid wood, and then the immune system comes along and throws gasoline and the steel rebar onto it.
It is the perfect storm for a persistent, indestructible biological obstruction.
Which brings us to the so what portion of the deep dive. Section 4. The impact on you, the listener.
Right.
Because most of us aren't lying dead on an embalming table. We're walking around, going to work, just living our lives. Why should we care about this chemistry?
Because while the embalmers are finding the giant macroscopic clots, the huge ones that obviously kill you living, breathing people, are very likely dealing with microclots.
Microclot.
These are the exact same chemical structure, just much smaller. But you have to remember, small is a relative term in biology.
Right.
Capillaries, which are the tiniest blood vessels in your body where the actual oxygen exchange happens with your tissues, they are only about 5 to 10 microns wide.
Very, very small.
But these microclots can be up to 200 microns across.
So do the math there. You're trying to push a 200-micron rock through a 5-micron tube.
It blocks the tube completely.
Oh.
And this leads to what we call hypoxic damage.
Oxygen starvation.
Exactly. The tissue on the other side of that blockage suffocates. It gets no oxygen, no nutrients.
And if this is happening systemically, all over the body, what does that actually feel like for a person?
It feels like your battery is permanently dead. The symptoms mentioned in the sources align perfectly with what people call long COVID.
Like brain fog.
Brain fog, exactly. Because the microcapillaries in the brain aren't delivering enough oxygen to the neurons.
Makes sense.
Extreme fatigue, muscle pain, severe exercise intolerance.
Because your muscles need oxygen to work and recover.
Right. If the capillaries are blocked with amyloid sludge, they can't clear lactic acid or get the oxygen they need to recover.
It's literally like trying to run a marathon while breathing through a tiny plastic straw.
And it creates a vicious self-perpetuating cycle called immunothrombosis.
How does that cycle work?
The blocked vessel causes local inflammation. The inflammation signals the body to call in more immune cells.
Right.
The immune cells show up, get stressed, and release more of those sticky nets. The nets stabilize more fibrinogen into more clots.
And round we go. A perpetual engine of inflammation.
Exactly. Until you find a way to intervene.
And that is the perfect segue. We promised a manual on how to dissolve the undissolvable. Let's talk about Section 5. The solution.
The therapeutic degradation strategies.
The source material calls this Systemic Enzyme Therapy.
Yes, SIFIS. This is the truly hopeful part of the research. We established earlier that the body's own enzyme, plasmin, is just too big and too easily inhibited by the Trojan horse to do the job.
So we need to bring in mercenaries.
Mercenaries from the outside, exactly.
Exogenous enzymes.
Specifically, enzymes that you can take orally as a supplement that can survive the harsh stomach acid, actually get absorbed intact into the bloodstream, and are biochemically tough enough to break down these amyloid plywood structures.
Okay, let's go through the roster. The first mercenary on the list is nattokinase. I've actually heard of this one. It's from soybeans, right?
Fermented soy, specifically a traditional Japanese dish called natto. Nattokinase is described in the literature as the general of this enzyme army. The source highlights a very specific triple action mechanism that makes it so unique.
Okay, what are the 3 actions of the general?
First, it acts as a direct fibrinolytic. It literally eats fibrin. It doesn't need to be activated by the body, it just circulates and chews it up.
Okay, direct attack.
Second, and this is crucial for the armored clots, it destroys the inhibitor, PAI-1.
It takes out the guard.
It completely disarms the trap. By cleaving and destroying PAI-1, it removes the chemical brake, which allows the body's natural mechanisms to start working again alongside it.
Oh, that's clever.
And third, it actively boosts the body's own production of TPA, or tissue plasminogen activator.
So it fights the enemy directly, it kills the enemy guard on the wall, and it rallies the local troops to join the fight.
Precisely. And the source specifically notes that nattokinase has been clinically proven to degrade amyloid fibrils, those hard cross-beta plywood sheets we talked about.
It can actually break them.
Yes. In the lab, it visibly reduces the pixel intensity of those glowing green clots under the microscope.
Okay, so nattokinase is the general. Who is next on the roster?
Serrapeptase. I like to call this one the drill.
The drill. Sounds aggressive.
It is a metalloprotease, and its origin is fascinating. It's derived from the bacteria found in the gut of a silkworm.
A silkworm.
Its biological job in nature is to dissolve the hard protective cocoon so the delicate moth can fly out.
So it has literally evolved over millions of years to break down extremely hard protective protein structures.
Exactly. The source highlights its superior ability to, and I'm quoting, dissociate complex amyloid structures.
How does it do it?
It acts as an endopeptidase. That means instead of just nibbling at the ends of the protein chain, it cuts right inside the middle of the chain. It chops the Lego tower right in the middle, causing the whole structure to collapse.
And does it play nice with nattokinase? Can you use them together?
They are very often used together in protocols. Serrapeptase is also specifically noted for breaking down biofilms.
Like the nets.
Remember those nets and the bacterial LPS components? Serrapeptase is excellent at stripping away that protective slime layer so that other enzymes can get to the core.
The source mentioned something about zinc and manganese when taking serrapeptase.
Yes, because it's a metalloprotease, its active site requires metal ions like zinc or manganese to function optimally.
Okay.
However, it is actively inhibited by copper, so your underlying mineral balance actually matters if you want this enzyme to work.
Okay, so we have general nattokinase, drill serrapeptase, and the third one.
Lumbrokinase, the sniper.
The sniper. Let me guess. Highly precise.
Extremely specific, and this one comes from earthworms, specifically Lumbricus rubellus.
Earthworms. Nature is amazing.
It really is. Lumbrokinase is a complex of enzymes that is reportedly up to 3,000 times stronger than the body's own plasmin enzymes in certain contexts.
3,000 times. That sounds dangerous.
It is incredibly potent, but the beauty of it is its high specificity. It only activates in the presence of the fibrin matrix.
What does that mean in practice?
It means it has a very low bleed risk because it doesn't just indiscriminately attack random proteins in your blood. It specifically hunts for the clot and only turns on when it finds it.
So it's a smart bomb, a bunker buster.
Correct. It degrades fibrin directly, and like nattokinase, it helps inhibit PAI-1. It is often considered the really heavy hitter for when nattokinase alone isn't moving the needle enough.
And then we have what I called in my notes the fruit salad strategy.
Yes, the botanicals. Bromelain from pineapple stems and papain from papaya.
Are these just mild digestive aids? I see them in the supplement aisle all the time. Or do they actually help with these massive clots?
They do genuinely help. Papain is specifically highlighted in the text for its unique ability to cleave all 3 chains of fibrinogen. the alpha, the beta, and the gamma.
Oh, wow.
It's a very broad spectrum cutter. And actinidin from kiwi and ficin from figs are also mentioned as potent degraders.
So eating a lot of fresh pineapple and papaya might actually be legitimately good for your microvascular blood flow.
It certainly helps support the overall systemic cleanup, though in these therapeutic protocols, they are usually used as concentrated add-ons to the really heavy-duty bacterial and worm enzymes.
Okay, so that's the enzymatic demolition crew. But you can't just blow up a concrete building without dealing with the dust and the rubble.
Right.
Which brings us to Section 6, supporting the cleanup.
Exactly. You need chemical allies to help clear the debris, and the biggest one mentioned in the literature is NAC. N-Acetylcysteine.
NAC. Now, I know this is a respiratory thing. A mucus thinner.
It's very famous for that. But do you know why it thins mucus?
No. Why?
Because it chemically breaks disulfide bonds.
Disulfide bonds.
The glue.
Exactly. Remember, those amyloid sheets are held together by very tight chemical bonds. NAC acts like a chemical solvent.
Okay.
If the enzymes are the jackhammers physically breaking the concrete, NAC is the chemical solvent that dissolves the cement, holding the individual bricks together.
Melting the glue. Melting the glue, yes. And it also actively reduces those sticky DNA webs, the nets. It's essentially a mucolytic, but for your blood in this specific context.
That makes perfect sense.
Plus, as a bonus, it is a direct precursor to glutathione, which is the body's master antioxidant.
Which helps cool down the overall systemic inflammation.
Correct.
Then there is methylene blue. This one always stands out for me because, well, it's literally blue dye.
It is a truly fascinating molecule. The source describes it as a metabolic enhancer.
Okay.
Remember the oxygen starvation problem we talked about earlier? The tissue hypoxia?
Right, the dead battery feeling.
Methylene blue actually helps the mitochondria, the little battery packs inside your cells, generate cellular energy even when oxygen levels are dangerously low.
Really?
Yes. It acts as an alternative electron carrier. It bridges the gap. It also actively inhibits platelet activation, which stops new microclots from forming while you're trying to clear the old ones.
So it basically buys the suffocating cells time to survive and recover while the enzymes are slowly clearing the blockage upstream.
That is exactly what it does.
What about diet?
Yeah.
Because we can't just supplement our way out of every problem.
The dietary anvil mentioned in the sources primarily focuses on curcumin, from turmeric and resveratrol.
The golden spice and the red wine compound.
These are crucial because they stop the underlying oxidative stress.
Which is the trigger.
The source states clearly that oxidative stress is the environment that makes fibrinogen prone to misfolding in the first place. By keeping the biological system cool with strong antioxidants, you prevent the formation of new amyloid.
It's basic fire prevention.
Exactly. And we shouldn't overlook the traditional Chinese medicine connection mentioned here.
Oh, right.
The source gives a very interesting nod to a classical herbal formula called Shufuzu Yu, or XFZY.
XFZY.
The ancient TCM concept of blood stasis correlates almost perfectly with these modern microclot findings.
Blood stasis.
Yes, this formula has been used for centuries to, in their terminology, invigorate blood and dispel stasis.
It's amazing how ancient empirical wisdom sometimes just catches up to or predates modern proteomics.
Or vice versa, yes.
True. Now, let's move to Section 7, Future Frontiers. Because medical science never stops, what is on the horizon for clearing these things if oral pills aren't enough?
One of the most interesting is sonothrombolysis.
Sonothrombolysis. That sounds extremely cool. Sound waves.
Yes, using specific low-frequency ultrasound around 150 kilohertz to physically shake the complex clots apart from the outside.
Like an opera singer shattering a wine glass.
Exactly like that. And to make it more effective, the source discusses adding magnetic microbubbles to the blood.
Microbubbles.
You inject these tiny acoustic bubbles and then you hit them with the targeted ultrasound. The bubbles violently vibrate and create these microscopic jets of fluid that literally tear the matted fibrin mesh apart from the inside.
That is incredibly high-tech.
It is. It's a pure mechanical disruption of a deeply chemical problem.
And what about plasmapheresis? I saw that mentioned too.
That is essentially blood filtering.
Taking the blood out of the body.
Taking the blood out, running it through a machine to filter out the inflammatory junk and the microclots, and putting the clean plasma back.
Does it work?
The source notes a lot of anecdotal success people often report feeling significantly better immediately, but it cautions that there is a distinct lack of rigorous, large-scale clinical evidence yet.
And there are risks, right?
Yes, you risk indiscriminately filtering out good, necessary proteins along with the bad.
So it's a bit of a blunt instrument compared to the targeted enzymes.
Yes, the enzymes are highly targeted biochemically. Filtration is just wholesale removal.
Okay, we've covered a massive amount of ground today. From the visceral shock of the embalming tables, to the molecular geometry of spike proteins, to the gut of a silkworm.
It's a lot to process.
Let's try to bring it all home with the outro. If a listener takes only one practical thing away from this deep dive, what should it be?
The synthesis.
The synthesis.
The source material heavily emphasizes that you cannot just do one single thing. It requires a comprehensive, multi-pronged approach.
Give me the final checklist.
Okay, number 1, enzymes. You absolutely need the nattokinase, serrapeptase, or lumbrokinase to physically eat the clot structure and disarm those trapped inhibitors.
Got it.
Number 2, NTC. You need this to break the chemical disulfide bonds and dissolve the biological glue holding it all together.
Right.
Number 3, antioxidants. Things like curcumin, vitamin C, and resveratrol to stop the ongoing oxidative stress that triggers the misfolding in the first place.
Fire prevention.
Exactly. And number 4, vascular support. Things like methylene blue to help your suffocating oxygen-starved tissues survive and heal while the pipes are being cleared.
So it's a full protocol, not just a magic pill you take once.
Exactly. It is entirely about changing the underlying biochemical environment of your entire bloodstream.
And here's a final, rather provocative thought to leave you with as we wrap up.
Yeah.
The source material suggests that these anomalous insoluble complexes might actually be a massive missing link in modern medicine.
Not just for things like long COVID.
Right, but for chronic systemic inflammation diseases in general.
It really raises a profound question about the future of human health.
It does.
If these extremely stubborn clots are easily induced by common environmental triggers, whether that's viral proteins, bacterial toxins, or maybe even severe chronic stress, are we looking at a future where enzymatic hygiene becomes as routine and important as brushing your teeth?
Enzymatic hygiene. I love that phrase.
Meaning, do we all need to start constantly helping our bodies clear out this microscopic inflammatory sludge before it builds up into something massive that an embalmer would eventually notice?
Right.
If we are simply living in a modern world that is full of these triggers, maybe we need to be highly proactive about the internal cleanup.
That is a thought that will definitely stick with me. We might really need to start thinking about our microvascular blood flow the exact same way we think about dental plaque. You have to actively brush it away every single day, or it hardens.
Precisely. It's a whole new paradigm for vascular maintenance.
Thank you so much for joining us on this deep dive. It was incredibly dense. It was undeniably a little scary, but hopefully it was highly illuminating for you.
Always a pleasure to unpack the hard science.
We'll see you next time. Stay curious and keep that blood flowing.